Now I pressed record right, or am I already record? Oh my gosh. Okay, awesome. Okay, all right, now we're going to do permutations where some objects are alike. So what happens now? Before we did permutations where all the objects were different. Now some are alike. So that changes things a little bit. So remember, the dictionary definition of a permutation is an act of changing the order of elements arranged in a particular order as ABC into ACB, BAC. Okay? So we did this yesterday, I believe, where I just rearranged three letters. And notice, when you arrange three different letters, you get 3 factorial equals 6. So notice there is 6 different ways to arrange 3 different letters. Now let's look at what happens if some letters are the same. Notice A is the same as is the same. Those two are the same, and B is different. So just to just so you can see what's happening, I labeled them A sub 1 and A sub 2. So notice you can have A sub 1, A sub 2B, and etc., and you can arrange those. But if we were to take a closer look, we don't always have subscripts for our letters. And in fact, we never have subscripts for our letters. We just use the letters, right? But I'm just doing it so that you can see that even though I arranged them and changed the order of all the letters, can you see that 1 is the same as 3, right? And 2 is the same as 4. And then these two guys are the same because it's BAA, BAA. The question wants, what the questions you'll see is how many different arrangements are there? How many different arrangements are there? So it would be nice if we could go 3 factorial equals 6, but it's not that easy. How do we handle when we have, for example, in this case, 2 letters the same? Here, in part B, the number of arrangements is 3, not 6. The number of different arrangements, notice different arrangements, is 3 and not 6. So what we do is the number of permutations of n objects, of which A objects are alike, another B objects are alike, another C objects are alike, and so on, is n factorial, and basically you divide by what's the same. If A letters are the same, you divide by A factorial. If B letters are the same, you divide by B factorial, and etc., etc. Applying this formula in part B, we have, there's 6 I think there's a typo here. This should be, there's 3 letters, 3 factorial ways to arrange 3 letters, and divide it by what is the same. Well, 2 letters are the same, that's 2 factorial, and that will work out to be 3. We divide by 2 factorial because there are 2 objects alike. 2 of the letters are A. So let's do some examples to reinforce this formula. Do you notice we are not interested in arranging these 2 letters? So in effect, we're dividing out the arrangement of these 2 letters. That's why we divide by 2 factorial. We're trying to cancel out the arrangement of those 2 letters. 7 sheets of paper are on Shannon's desk. There are 4 sheets of blue paper, one each of red, yellow, and green. In how many ways can she stack the papers when she tidies her desk? Okay, so really, in how many different ways? Okay, so we assume that the four sheets are identical, right? And then she has three other sheets, all of a different color. So anyone want to give that a try? The number of arrangements equals what? Huh? And how did you get that? That's right. 7 factorial divided by 4 factorial, and you just plug that into your calculator and you get 210. Consider the word logo. Determine the number of arrangements by writing it out explicitly. We're not going to do this one, creating a tree diagram, and I think it's a bit much, and using factorials. Okay, let's write out all the arrangements explicitly. So notice we are going to have how many arrangements? Well, let's list them. Number 1. Well, we'll start with logo. That counts. Then we're going to have lug. Then we're going to have agu. I won't try to pronounce it. Gu, right? We're going to have 0LGO or OLGO. And it's hard to list all of them to make sure you get them all. And then we'll have GLOO, 7 GOOL, 8 OGOL, 9 OGLO, 10 OOLG, 11 OOGL, 12 OLOG. So there are 12 different arrangements. And then here using factorials, well, that's the easier method, right? We just go 4 factorial. We have 2 items the same, 2 factorial, and that equals 12. Different arrangement. Okay, let's keep on going. Can I elaborate on anything or explain anything better? It's good? Okay. How many permutations of the word substitute begin with I and end with B? All right. Well, let's see. Let's analyze our letters a little bit, because if you notice, some of them are the same. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters. Now let's see. We have 2 S's, or 2 the same of those. We have 2 U's. We have 1 B. Okay. We have 3 T's. I'm going to just write it down, 1B, so I keep track of everything. S's we had 2 S's, and we had the U. So we have 3 T's, 1, 2, 3, 3 T's. Just keeping track, let me just fix that. We have 3 T's, and we have 1 E. Let's just make sure we have them all. 4, 5, 6, 7, 8, 9. Which one am I missing? I? 1 I. Okay. Okay, good. So how many permutations begin with I and end in B? So this beginning with I and ending with B, those are restrictions. So you do the restrictions first, and then we're going to fill in the rest. So there are 10 letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It has to begin with an I. So that's one letter gone, right? There's no choice. So that's why I put the number of choices is 1. And it has to end in a B. So again, there's no choice. So my I and my B are gone. How many letters does that leave me to work with? 8, right? So I have 8 letters to play with. So it's going to be 8, 7, 6, 5, 4, 3, 2, 1. So 8 letters to choose from in the first position and 7 in my second. It's like these are kind of history, right? The choice is done, they're gone. Let's focus on what we have left to arrange. So we're going to have 8 factorial, and we're going to have to divide by what? 7? Or do we do 7 factorial? We divide by 2 factorial, right, for the 2 S's, 2 factorial for the 2 U's, and 3 factorial. And we should get 1680 arrangements. It's a little bit tight in here, but how many permutations of the letters of Mississauga do not start with S? So this do not start with S is another restriction. So remember, do the restrictions first. Always do the restrictions first. That applies here because that's a restriction. Now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. Right? And so let's analyze it. We have 1 M, 2 I's. Let's see what's the same. 4 S's. Oh, 2 A's. 1 U and 1 G, if I'm correct. Looks good. Okay. So let's see what that might look like. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There is no S here. No S. So how many letters do we have for that first position? See how I'm doing that restriction first? I'm handling the no S in the first position. They do not start with S. So then I have how many letters left to play with? 7, right? Because there are 4 S's. So we go 11 minus 4 equals 7. So I have 7 letters to play with there. How many letters do I have for the next position? Yeah, so it's 10, 9, 8, all the way down to 3, 2, 1. Okay, so let's do it and we'll divide by what's the same. We have 7 times 10 factorial over what is the same. 2 factorial, 2 factorial, 4 factorial. And if we work this out, we are going to get 264600. So 264,600 different arrangements. That's just our rough work. That's analysis of our letters so we know how to handle the question. Oh, here's another one. Isosceles. Let's check it out. Have C in the middle position? Well, let's analyze it. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. We have one I, 1, 2, 3 S's, one O, one C, two E's, I think. 1, 2, 3, 4, 5, 6, 7, 8. Oh, we have 9 letters, so I'm missing something. One L, 4, 5. Yeah, now we're good. We've got them all. Okay. So again, 9 letters. 1, 2, 3, 4, 5, 6, 7, 8, 9. So C goes in the middle. Again, do the restriction first, and then we can play with the rest. So, or arrange the rest. If C is gone, we're down to 8 letters. So we have 8, 7, 6, 5, 4, 3, 2, 1. So it is a little bit tight here. I guess what I'll do is I'll write it down here. 8 factorial divided by what's the same? 3 factorial, 2 factorial, and that equals 360 different arrangements. I'll put a period there. My ments won't fit in there. Okay, permutations begin with O but do not end in L. Oh brother. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. So begin with O. Our O's gone. No L. No L. Okay. So we can't use an O and we can't use an L. How many letters do I have to play with here? 7. Now I used up another letter. Out of my 9 letters, I've used up 2. So there are 7 left to play with. So it's 7, 6, 5, 4, 3, 2, 1. So it's going to be 7 factorial. Divide by what's the same? 3 S's and 2 E's. And that equals... Uh-oh. I forgot. Perfect. Thank you. And that equals 940 different arrangements. The permutations have E's in adjacent positions. Well, let's just sort of draw that out. We got E's. So if they're beside each other, it's like I'm going to put a box around them. Because they're moving together, I'm going to treat them as one character. And then those are 2, 3, 4, 5, 6, 7, 8, 9. So we have 7 letters left to play with. Oh, but we're arranging 1, 2, 3, 4, 5, 6, 7, 8 things, right? Because we're also left with, once the E's are gone, we're left with I, S, O, S, C, L, S, right? So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 items we're arranging. And we have to divide by what's the same. So there's 2 factorial ways to arrange 2 letters, right? But we're going to divide by 2 factorial because the 2 E's are the same. And then we're going to divide by 3 factorial. And this works out to be 6720 different arrangements. Okay. Can I explain anything better? Anything that is puzzling you or no? Good? Okay. Thank you. Have a great break. Bye bye.